What's up, everybody? This is Matt Brown with another IoT hacking video. Today we have my master built charcoal smoker control unit once again over on the workbench. Today we are going to be doing some firmware modification. Last time we extracted the firmware from the ESP32, and today we're going to be modifying that firmware with a very specific goal in mind, and that is intercepting TLS traffic from the grill to the backend AWS cloud services. So stay tuned to the end, and we're going to go all the way from firmware modification, intercepting TLS traffic, to a Python script that can hit AWS APIs with those creds and interact just as our grill would to get information about our grill. So first, let's go over to the workbench and let's remind ourselves of the setup that we have. So if you remember, I had this unit that I bought off eBay that was kind of sketch, maybe a dev unit, maybe fell off the truck, who knows, but we are actually performing all this work on my actual grill unit taken from my functional grill. So if we brick this, I'm out my charcoal smoker. So we'll try not to do that today. So, and then we have like our really simple UART setup over here. And if you guys remember from the previous video, we have this jumper that we'll be kind of taking in and out of this situation. And that's because there is a GPIO pin that is mapped. Let me get my tweezers so I can kind of point. So if we zoom in here, we have a GPIO pin that is mapped to GPIO 0 right here, and it's mapped up here, and then on my little breadboard up here, tiny little breadboard, right here, this kind of second pin from the top, that is where that GPIO pin is mapped. And we read in the video from the documentation that if you bridge this pin over to ground, which I have right here, then what we can do is we can put it into bootloader mode and we can read and write firmware on our ESP32. So that's our setup. Right now we're just going to have this be disconnected. This device is actually live and running, and let's go take a look at the UART console. So we do have that cable. Again, it's just a standard 3.3 volt UART cable, and it's running at our most common baud rate, which is 115/200, and then on my Linux machine, that's going to map to dev TTY USB 0. And we can see that, like I said, this device is powered on, and we are seeing all sorts of interesting traffic here. I think it's actually gone to sleep, but if I scroll up here, you'll see from the previous output of the UART console that we got all of this helpful information about what data is being sent to these AWS Thing APIs, right? So AWS has these services for IoT devices that are specific MQTT endpoints that kind of provide structure for you to put and get information about a thing, an IoT device, right? And so we get a lot of cool information from this, but sometimes, like most of the time, you're not going to get this detailed of information over the UART console. You're going to have to somehow decrypt what's going on over the network. So let's actually look at what's going on over the network. First, I'm going to talk about my setup. I've talked about this in previous videos, so I'm not going to go over this too much, but I am using my man-in-the-middle router setup where I have a access point, as we talked about, that's being hosted on my Linux machine here, and then that allows the grill to connect to the SSID that is being hosted here with host APD, open source Linux router software. And so that's connected to a bridge interface, which we will soon go over and look in Wireshark, and we'll be sniffing on this interface. And so then in my whole setup here, there are some optional IP tables rules. So right now, those are all disabled. So my computer is just acting as a router, and it's hosting a wireless access point, and it's routing that traffic through to the internet on the WAN port. And so let's go over here. This is where I'm running my man-in-the-middle router setup. And we can go here and look at Wireshark, and I can kind of scroll up into the past here and see some of the communications that this device has. So here we see a DNS request to some big long thing, .iot.useast2 Amazon AWS.com, right? So there we can clearly see that there is communications, the DNS request being made for this domain that is obviously the IoT specific domain that this device is reaching out to. And then we see a SYN packet using TCP to port 8883. So if you're not too familiar with looking at network traffic from IoT devices, you might just be used to web that usually operates on 80 and 443, those ports. Well, 8883 is a common MQTT port. And so that is the protocol that we're going to be trying to see after we get inside of the TLS tunnel. Obviously right now, we cannot get to the MQTT traffic because we have TLS, right? So we have a client hello, we have a server hello, and then let's filter on TLS and let's just look at the TLS messages because this is going to tell us something about what we need to do if we're going to perform this TLS interception. Something extra than we might need to do under normal circumstances or most circumstances. So we see a couple of these certificate messages. We see 2 certificate messages, which is somewhat unusual if you're just used to looking at normal TLS traffic, right? It is usual, let's expand this out here. So here we have the public IP, so this is the cloud server, that is sending its certificate to us, our IoT device. And that's normal, that's totally normal. And we can actually, on this packet, we can actually drill down here and see what this certificate is. We can say, probably want to look at the leaf down here. We can say signed certificate. We can look at the subject and the common name. So there we go. Okay, we have some kind of a root CA here, and we can obviously look at the other stuff. I'm just going to scroll through the hex view. You can find right here that we have the Amazon CA server cert here that's being communicated. Let's try to find that. Yeah, there's a bunch of information about it. Here we go. Amazon root 1. That's our guy. That's it right there. Okay, so Amazon root CA1. This is a very common root CA here. Okay, this is an Easter egg. This is a total aside thing here. Can I find it? So it's really funny. So this certificate, its expiration date is really kind of funny. I can't find it. It's a little Easter egg. It's a few days away from a very significant event that will happen in the technology world, kind of like a 2000 event type thing. So go ahead and look that up in your free time. So anyway, back to our TLS message. So we saw that certificate. That's normal. But here we see the client sending a certificate to the server. This is telling us that mutual TLS authentication is occurring. So standard part of TLS communications is that the server proves that they are who they say they are to the client, right? When I go to google.com, my client better be verifying that the site that says they're google.com actually is google.com, and they do, and your browser does that by verifying the certificate. Optionally, in the TLS protocol, clients can authenticate themselves to the server. Now, typically, when you go to Google, Facebook, whatever it is, the way you authenticate is not through a certificate. It's not at the TLS layer. It's at the application layer that's inside that TLS tunnel by using a username and password, right? But especially for IoT devices, it's a lot easier to just authenticate at the TLS layer with a client key and certificate pair. And so that's what we see going on here. And that means when we set up our interception tools, not only are we going to have to configure the CA to be our CA that we control, but also we're going to have to pass our interception tools if they want to connect upstream to this server. We're going to have to give those intercepting proxies, man-in-the-middle proxy, SSL split, we're going to have to give those tools our client certificate and key so that it has access to those, so that it can authenticate upstream and re-encrypt our traffic up to the server. So this is cool. We've got a view of this now. Now let's jump into some firmware modification, which is the first thing that we're going to do. So we have our firmware dump here. In our last video, we used the ESP tool program to pull the firmware off of the ESP32 on our grill device. So let's go and look and learn a little bit about the partition table. So there is a partition table at a very standard offset. So we can see here it defaults to hex 8000 in the flash. And then it gives like a size. It says, it's usually 4 kilobytes. I think I have a command that we're going to run here that reads a little bit more than that. That's not that important. But suffice it to say that we're going to carve off the partition table starting at this offset of hex 8000. And so let's go over here, and I'm just going to pull up a command that I've got over on the other side. Okay, so here we go. We have this dd command, and what we're going to be doing is our in file, our input file, is that initial firmware dump, and then we're going to carve out, we're going to have the output file be called just partition table, and again, we're skipping hex 8000 converts to this number right here, and it is just going to read the 1000 hex or 4096 bytes. So we're going to carve that out. Good to go. And now we're going to use this tool to read out the partition table. So kind of back a directory here, I'm going to show you. I have this ESP-IDF repository. So this is something that I've grabbed off of GitHub here, and it is just a, kind of like a development kit, an SDK for the whole ESP platform. So obviously you can build firmware for these devices with this SDK, but there's also lots of tooling that help you debug things. So there's some helpful Python scripts that we find in this repository that we'll be using in this video. So that's just a reference for why I'm going back a directory into this random repository. So here we go. We're going to, nope, not that command. I'm going to paste this command here. So we're going to run this gen ESP32 partition tool. And so we're going to run that. And it's going to parse this partition table and give us a bunch of helpful information about the different partitions inside of the flash image. And so the thing that we are going to be focused on today is right at the top. It is this NVS partition. So NVS, what's that? And then we can see the offset is hex 9000, and then there's 16K worth of data inside of this partition. Well, what is this thing? So we go over here and we can look this up. ESP32 has this NVS partition, this non-volatile storage library. It is effectively a key value store that exists in Flash and has some optimizations for where leveling. It does journaling and things like that, so it's not always reading and writing to the same place. I'm not an expert on Flash architecture, so you can correct me in the comments of this video if I said anything wrong there. But okay, cool. There's this standard for storing data, data that's meant to be, read and written to. That's meant to be updated in code. And so that is what this whole NVS partition thing is all about. And so I started looking around. I'm like, okay, it's cool. There's some tools for us to interact with this. The answer is there's some tools out there to read out some information, but I ended up kind of vibe coding my own solution to that. So over here, I have a repository that I'll put in the link, the description in this video. And so what we have here is a couple of Python scripts. And this first one, NVS read, what it's going to do is we're going to take in the NVS partition, and it's going to figure out all the data that's stored in there. And then we're going to convert that. So I'm just kind of walk through the step. Then that's the first step, is we're going to unpack all the data that's inside this NVS partition. And then we're going to convert it to a CSV format. Why would we want to do that? That sounds like a bad idea. Well, because that same, the SDK I just mentioned, they have an existing tool that will take this CSV format. We'll talk about it more in detail in a minute, but it's going to take that and it's going to regenerate it as a valid NVS partition, the binary image file. And so this is going to help us, because then we can put it in that format and then we can make modifications. We're looking to modify things here in our firmware today. And then we can repackage it and we can smack that all back together inside the firmware image, and we can upload that and write it to our device and hopefully have a successful firmware mod. So that's the process. We're going to go into detail in a little bit. So the first thing we're going to do is, using the data from that partition table, now we can carve, using DD, we can carve out just that NVS section, and by doing, skip the offset and then count the size. So now we have our NVS bin file, and we can run strings, and we see all of our data. We see my Wi-Fi password, just like we did before, right? We already saw this inside the larger image before. So now what we're going to do is we're going to use that tool that I have now in my open source repo, and we're going to read out all of the key and value data into this JSON format, okay? And this is straight up written by Grok, with some nudging by me to tell it how terribly wrong it was at first. I'm not worried about AI taking my job anytime soon, don't worry. But yeah, so it outputs it in this format. So in the key value store, there's a couple things. There's basically two different kind of types of things that you can store. You can store these namespace definitions. So the namespaces are basically so you can have two different things that are called key, two different keys in the key value store that are called key, and as long as they're under a different namespace, they don't conflict, like a directory or something. And so, and then we can see, it's just storing information that it's extracted out of this NVS partition. And so next, what we're going to do is we're going to convert it to that CSV format. So we're just using that other Python tool that we generated to convert it to the CSV format. And you'll notice my tool outputs something else that says blob files are stored in blobs. And what that means is the directory. So it just created this directory, blobs, that now has a bunch of binary, it has a bunch of data in it, right? And so this is important because if we go over to our tool here, not that one, this one, so this partition generator utility. So this utility is, again, it's targeted at developers, not firmware hackers or whatever. So the whole point of this is so that manufacturers, when they're manufacturing individual devices, they can just have a CSV file, right, that has maybe the device unique information, right? Maybe you need to, on the assembly line, you need to flash a unique serial number, a unique MAC address, a unique set of credentials, an RSA private key, perhaps. You need to flash those individually, and so what you can do is you can put those all in the CSV file, and then you can generate all of this partition data, and that way you have this unique firmware that you're able to flash to each device on the assembly line. Anyway, the way this works is that they kind of have an example here in test data, and so here is an example of the CSV file, and you can see that there are certain blob types here that refer to a file that is basically inside of that directory, right? So you can put, short string data right here inside. Here's, like, for example, here's a string that's just in the CSV file itself. But if you have a really large, binary blob of data that you want stored as a value in the key value store, then you put it in this external file, right? And so that's what it expects, and that's what we're going to give it. So that's why there's all these blobs. that our tool generates. So we now want to modify one of those blobs. Well, which one is it? Well, let's go through our data CSV file, and let's look. Right down here at the bottom, we have CER, key, and CA. So the key file is definitely something we're interested in, but for another purpose, and that's because we need this, because this RSA private key right here, you can OCR this right now, and you, at the end of this video, you too can check the values of my grill and what temperature I'm cooking my meat at. All right, so what we're gonna do though, that's not what we want to modify, but I have that, I've extracted that out to use later. So what we want to modify is this CA right here. So I'm gonna copy that out. And this certificate we want to replace, and I'm going to just open another little window really fast inside my man in the middle directory setup, you know, a little foreshadowing here. All right, and so I'm using the man in the middle proxy, CA certificate, and I'm going to copy this out because we are going to replace that right here in our blob file. Okay, that can go away. And so what we're gonna do is now we've replaced the, you know, that Amazon CA, right? Or you know, remember over here, we're trusting in this Amazon root CA. And so when I intercept with my proxy, the proxy is not, like, I can't present Amazon root CA1 because I don't have the private key for that, right? But this man in the middle proxy setup right here, right? I have the corresponding key to this certificate that I'm going to put inside of the modified firmware, so that way the device trusts my CA certificate so that I can intercept and get inside that TLS traffic. So that is the goal. And so next what we're going to do is we are going to use that ESP SDK's tool, this partition generator, and we're going to pass it the CSV, and we're going to have it generate a file called mod NVS. And so there we go. We're using this v2 multi-page blob format, which I don't know if that matters, but we're using it. So now we have this modified file right here, and then we are just going to copy the original firmware file over and just call it mod.bin. So it's going to be our modified overall firmware file. And then what we're going to do is we're going to run this dd command, and we're going to be copying our modified NVS partition into the right place inside of the new firmware file. And so it will place our modified partition right where it needs to be, and now we can upload it to the device. Cool. So next we are going to use the tool here, and we are going to flash it. But right now it's not in the right mode. So let's come over here, and we're simply going to, okay, I'm going to turn off the device off screen over there, and we're simply going to put this jumper here. So now that's ready to go, and over on our screen, what we're going to do, I haven't powered it on yet. I'm going to just hit this so that it's like trying to connect. Power it on, and it will begin our firmware flash. It may take a while, as it says. We're writing data. All right. So as this writes, let's just talk over what we did. Big picture. Yeah, so we have the NVS partition. We extracted it. We found that CA certificate. That is the root of trust. When our device reaches out to the cloud, it says, that's the certificate I trust. And so now we have our one that we control, trusted by the device. So hopefully, if all goes according to plan, now we will be able to proxy that in our man in the middle proxy setup. Actually, this is a great time while we're waiting for that firmware to flash to come over here, because we're going to have to come down in our man in the middle proxy script here and uncomment this line here that I have all ready to go. So this is an IP tables rule that is simply going to look for any traffic that is going out to 8883. That's the MQTT service, and it's going to redirect it locally to 8081. And so what we're going to have running here, let's get that set up, is, yeah, let's do that. And you can see all of my working directories here. Awesome. Where the heck are we, guys? Firmware mod. Sweet. So we're going to get our man in the middle ready right here. Can't type. All right, so we can just set this up. So we're going to use man in the middle dump first, but we're just going to or man in the middle proxy, because let's just use man in the middle proxy first. Okay, so now man in the middle proxy is listening on 8081. Man in the middle router is redirecting all traffic that is outbound for 8883 to our intercepting proxy, which should be trusted by the device. So if all goes according to plan, we should be able to intercept traffic. So here we go. It's telling us, okay, it's done. I'm going to turn the device off. I'm going to remove my jumper. And then I'm going to just get ready over here to observe any errors, because the errors kind of flash decently quick. Actually, let's use this right now. Oh, I have to run the network. Haha. Okay, actually, what we're gonna do. Okay, authenticated. The device connected. That's cool. Let's reconnect. Ecocom. Go. Okay. Getting stuff. Deauthenticated. Fun times. All right. Let's try turning it off and on again. That helps. Sometimes it helps. You'd be surprised. All right. There we go. What is going on? So one of the things that I've definitely noticed about this grill is that it constantly loses its cloud connection, and I have to factory reset it, like in the normal operation of the grill. This is just something I've noticed. So we may have to rev this a couple times. All right. Yay, read in the key insert. Why is the Wi-Fi disconnected? All right. All right, we're just going to see if SSL split is any more luck. And let's check our packet capture also. All right, we're going to reboot again, just for the heck of it. Wi-Fi password is wrong. No, it's not. There's the clear text password. Yeah, I swear this happened last time too. It just will sometimes not connect. Because at a minimum, I should be getting like SSL errors here. All right, we're gonna go down. Yeah. And then we're gonna go up. And then we're gonna power cycle again. Wi-Fi disconnected. Try connect. Yeah, it's deauthenticating. That's weird. Yeah, that doesn't matter. All right, let's try one more time. Because why not? Hey, okay, that does something. That does something when I like power it on and then power cycle it. All right, we're learning the hacks. Okay, so here we go. It is connecting to AWS. I mean it is, and we are getting stuff here in our intercepting proxy. Okay, so it is telling us that we are successfully intercepting things. So just so we can like kind of understand what this command is doing, let's scroll up and take a look at it really quick. So SSL split. So SSL split, like man-in-the-middle proxy, is a intercepting proxy or a transparent proxy. So it is going to take TLS communications that come its way, and it's going to attempt to terminate them, and it's going to attempt to on the fly generate a like fake certificate that is signed with the man-in-the-middle proxy CA key and CA cert, right? So it's going to use those to sign any of the forged certificate that it's creating to pretend to be the AWS service, and it's going to write all of the data into this PCAP, which is really nice. So let's go ahead and I'm actually just going to close out of this, and we're going to, open up that PCAP. So now we have cap 1, and we're going to send that over here and take a look at this together. So here, this is kind of a synthetic PCAP. That's what you have to understand with like SSL split. So if you're looking at like the individual TCP packets, they're not going to make a whole lot of sense, right? Like it can't see the Ethernet layer, right? So it just makes up MAC addresses, right, on the Ethernet layer. And so you can just like take some of that stuff with a grain of salt. But what we are interested in are the flows, right? So if I just kind of click through the packets here, you can see that we have actually, that's like off screen for you guys. That's hilarious. All right, you can see here, now you can see right over here that we are actually getting clear text data that was inside of that TLS tunnel, but because we're terminating TLS with our intercepting proxy, we are able to see inside of these packets. So we can go right click, we can say follow TCP stream, and I can't make that any bigger, which is fun, but you can see here that, well, I can see it, the endpoint, the MQTT endpoint that is getting hit. And we can actually go back here, and this packet right now, it's just being called TCP, but we can, in Wireshark, go and right-click and say decode as, And then we can say, okay, packets that have 8883, we can decode those as MQTT. We can hit OK there. And now it can start to parse these as MQTT packets, which is super helpful. So let's just make that nice and big. And let's look through some of these packets. So here's a connect command. Okay, I don't care about the TCP layer. Here we go, MQTT layer. Here we go. Here's my client ID. So that's a client identifier, right, that identifies my device uniquely in the AWS IoT ecosystem. And so we can look through other cool MQTT packets. So right here, we're getting a job. We're like saying get job. All right, I'm going to look for a specific request, right? I think this is it. It's like get rejected, but get accepted. Actually, let's do a fun little and MQTT. So let's just filter for MQTT packets and just get rid of that part and say, yeah, show us all your MQTT packets here. So here, yeah, we see the reference to this like shadow/get. And so if you're familiar with like the AWS IoT ecosystem, that's basically like a way that says like, hey, get me all of like the information about the device. So we're starting to get, you know, API endpoints. We're starting to get these which are called topics in MQTT. So you can see down here, we have this topic of AWS things, our identifier, shadow, get, rejected. And so we can understand now, we know our identifier, we have the key, so we have those authentication credentials now. So now, the really cool thing about this is we can write a Python script that will take, you know, that now we can make requests directly to the API as if we were the device. So that's what we're gonna do now. I'm gonna come over here and I'm going to exit out of that. Yeah, obviously here we have, you know, the blessing of even in UART we can see what some of these requests look like, right? So so what I have done is I have so now we were able to, you know, intercept TLS. That was a pretty big accomplishment. Now what we're going to do is we're going to transform some of that data that we saw inside the TLS pipe into a script where we can reach out. So that's what this little Python script is going to do. It's going to use the, you know, the PAHO, I don't know how you pronounce that, the MQTT library, and we're going to take in a cert, a key, and a CA cert. We don't really need the CA cert. We could just tell it to like not worry about the CA cert because we're the client, but we'll do that just for the heck of it. But the client, the certain key, those are the credentials that we pulled out of the key value store. The CER and the key value, those are the device-specific credentials that my grill only has those keys that we extracted out of the flash. So in here we can see the broker host name, the thing name that again we've kind of extracted that from everywhere. We have port 8883, and what we're going to do is we're going to publish to AWS things, our thing name, our thing identifier, shadow get. So the shadow, it's like kind of just says like get all the data about this thing. Give me all of the data, the JSON blob about this device. And then it has a whole bunch of other stuff that's going to do all the things. So basically what we can do, we can run this command where again, we're passing it authentication credentials, and we can hit that Amazon API, and we now can independently of the embedded platform, we can interact with the API ourselves and do all sorts of fun things. We could potentially change, you know, what the grill temperature is set to. So here it says heating is false, right? We could turn the heat on the grill, and the intensity, the trigger. I don't know what all these things are, but there's also the interesting like min and max values. I don't know what would happen to the grill if we start messing with those. If you could like increase the top end threshold that the grill would heat up to, that could be, you know, potentially dangerous. Obviously, this is an advanced supply chain attack where, because the keys don't change, we discussed this in the last video. This set of credentials, this client key that I have here, and I'm going to cat out again for all you people at home to use. There it is. You can OCR that. All right. So this key, it doesn't change when you factory reset, right? So what if I was to give this grill to somebody else? Well, now I have credentials and I can mess with their device, right? Or, more like the eBay scenario, if they would have sold me a functional device on eBay, not this piece of crap, but if you can, take one of these, read the keys off, and then resell it online, well, now you have access to somebody else's device because the setup process is not creating a new set of key material when you create the device. So thank you for watching this video. I hope you enjoyed it as much as I did. There's a lot of work, a lot of reverse engineering to figure this out, and sometimes it's not straightforward, but I really get excited when you finally get that. You finally see the firmware modification work without the device crashing, where you finally get the traffic to get intercepted when you're dealing with a bunch of hardware problems. So I get passionate about this. I'm glad you have watched to the end. Thank you, and have a good day.